Okay, in this lesson we're going to talk about zeros of polynomial functions. So let's start off by defining one. A polynomial function is a function that can be written in the form p of x equals a sub 0 x to the n plus a sub 1 x to the n minus 1 plus a sub 2 x to the n minus 2 plus any number of terms in between plus a sub n minus 1 times x plus a sub n. Which this can look kind of intimidating, so let me try and help break it down for you. Well, first off, I've got p of x instead of f of x. We can use f of x, g of x. The letter that we use for the function doesn't make any difference. Here we're using a p simply because it helps designate that this is a polynomial. All right, the a sub 0, a sub 1, a sub 2, a sub n minus 1, and a sub n, these are all just constant values. And so you can have any number of constants which are making up the coefficients of your polynomial. And so instead of saying a, b, c, and so forth, we are just using subscripts of a to designate different multipliers. So they're just numbers. The n, n minus 1, n minus 2, those are the powers on your variable x, and those are descending in power. So if you started with, n equals 4, then 4 minus 1 would be 3, 4 minus 2 would be 2, and so forth. So these are just simply representing the descending powers of your exponents. Okay. Now, there are some parts here that are more important than others. So for instance, a sub 0 is called the leading term coefficient. So it's the coefficient on the term that has the highest exponent on the variable. A sub n is called the constant, and that's going to never have an x multiplied by. It's just going to be just a number. N is called the degree of the polynomial. So whatever the highest exponent is out of all the terms, that's the degree. So that's labeled n. So for example, p of x equals 6x cubed plus 5x squared minus 2x plus 4. This is a perfectly valid polynomial. It fits into the rubric that we set up in the above function. And we've actually studied polynomials before. Some polynomials we've already studied. The constant function, f of x equals c. So this is the simplest form of a polynomial function, and it's designated as having degree 0 because there's no exponents, there's no variables, so you have a constant with just degree 0. Linear function, y equals mx plus b. This qualifies as a polynomial function as well. It's one of degree 1 because the highest exponent on my variable is just 1. And the quadratic function, f of x equals ax squared plus bx plus c, is a polynomial of degree 2. So we've actually learned already quite a bit about polynomials. We just haven't really called them that yet. Some other interesting things that are useful. First off, for any polynomial function, the domain is always negative infinity to positive infinity. So that's something to kind of keep in mind. We don't really talk a whole lot about domain and range for polynomials, but it's kind of nice to know that in general, for all polynomials, the domain is always that right there. Okay, let's get into some theory. So starting with what's called the factor theorem. So x minus k is a factor of the polynomial p of x if p of k equals 0. So what that means, if you can take the value k right here, plug it into the polynomial function x, so you plug it in right here. If that results in 0, then you have a factor of the polynomial. Or equivalently, x equals k is a 0 of p of x. So if x minus k is a factor, x equals k is a 0. So these are equivalent statements here. Notice, however, the use of positives and negatives. So it isn't like if you have x plus 2 as a factor, then what that means is x equals negative 2 is a 0. So it's always kind of the opposite of this number because of that negative right there. We'll get into that as we move forward. So let's start off by showing that x plus 3 is a factor of p of x equals 6x cubed plus 19x squared plus 2x minus 3. Well, I could plug negative 3 into my polynomial and evaluate it. However, we learned in the last section that you can actually do the same thing easier by using synthetic division. So that's what I'm going to do. 6, 19, 2, and negative 3. So if I bring the 6 down, 6 times negative 3 is negative 18. Negative 18 and 19 is 1. So that becomes negative 3. And that becomes negative 1. Negative 1 times negative 3 is positive 3. And these add up to 0. And because this evaluates to 0, this says x plus 3 is a factor of p of x. Okay. What we can say now is, okay, so we've taken the polynomial 6x cubed plus 19x squared plus 2x minus 3, and we divided it by x plus 3. So that was the, that we did synthetic division. That's what that means to do. And if we take these coefficients, that gives us a resulting polynomial, and there was no remainder. So we can say that this evaluates to 6x squared plus x minus 1. What's more is if I multiply both sides of this equation by x plus 3, it cancels in the denominator here, leaving me with just 6x cubed plus 19x squared plus 2x minus 3. And then there's nothing to cancel on the other side, but I can write it as x plus 3 times 6x squared plus x minus 1. And effectively, we found one factor of a third degree polynomial. So we can express this polynomial equation in this form right here. This is a factor. The x plus 3 is a factor, so we've essentially factored a third degree polynomial. This is the starting point of the process that we're going to be doing throughout this chapter. What's more than that is we're now just left with a second degree polynomial, which is a quadratic, that we know how to factor. So we can say, all right, 6x squared plus x minus 1. Well, let's see if we can factor that. Well, 6 has two possibilities, but for 1 and 1 are the only options. 6 could be 1 and 6 or 2 and 3. If I need these things to add up to positive 1 here, this coefficient, I think 2x and 3x are going to be the choice here. And so I need the 3x to be positive and the 2x to be negative. And that works out because 2x times 3x is 6x squared, so that works. 2x times negative 1, and let me write this out. So 6x squared minus 2x, so that's good. 1 times 3x is 3x. And 1 times negative 1 is negative 1, so it does factor. So 6x squared plus 3x minus 1. So all I've done, oops, not plus 3x, just plus x. So all I've done is factored that polynomial. Okay, which means we have fully factored a third degree polynomial, because now what I can do is just write it in this form. So I can just write 6x cubed plus 19x squared plus 2x minus 3, which we knew was equal to x plus 3 times 6x squared plus x minus 1. But then we factored that into 3x minus 1 times 2x plus 1. And now we have this polynomial, this cubic polynomial, fully factored into linear factors. That's our overall goal for this unit. Now, we're going to need some help with some theory. So let's take a look at the next slide here. We're going to discuss the fundamental theorem of algebra. It's pretty straightforward. It says that a polynomial of degree n will have exactly n zeros, which shouldn't be too surprising. We've kind of hinted at this before. When we had a linear equation, it was degree 1. There was one solution, so it had 1 0. When we had quadratics, it was degree 2, so it had 2 solutions when we solved those, 2 zeros. The only thing that's slightly complicating is that these may be rational, which like, you know, a over b, like a fraction, or an integer counts as a rational as well. Irrational, meaning, you know, square roots involved. Imaginary, so like, you know, I, okay, or repeated zeros. Repeated zeros are a little bit tricky. We call those multiplicity of zeros, and we'll talk about those cases as we get there. So knowing this, we basically have to find enough initial zeros so that when we factor out each known zero using synthetic division, we end up with a quadratic, which we can then factor, or if we need to, apply completing the square or the quadratic formula, whichever the case may work for you best. So how do we find initial zeros? One way is through the rational zeros theorem. Another way is through the calculator. We're mostly going to use, well actually we're exclusively going to use the calculator to help get initial zeros. But I'm going to go through the rational zeros theorem so that you know how it works, and in case you need to use it at some point. So let's begin there. Well, the rational zeros theorem says, if f of x is a polynomial function and p divided by q is a rational number written in lowest terms and is a zero of f of x, then p is a factor of the constant and q is a factor of the leading term coefficient. This is essentially generalization for any degree polynomial of the factoring process that we do, you know, starting, you know, if you're trying to factor, say, like x squared minus x minus 6. You know, you're looking for two numbers that multiply to the constant term and then add up to the middle term. Well, so basically, you know, what we're doing is listing out factors of the constant and the leading term coefficient. So plus or minus 1, plus or minus 6, plus or minus 2, and plus or minus 3. So we're kind of doing this mentally, but we're getting a list of all the different possible factors and then just trying them all to see what works. So this is just a generalization of that type of a process to higher degree polynomials. So let's see how it works. It's pretty straightforward to get the list at least. So let's say we want to list all the possible rational zeros of this polynomial function. What we would do is list out factors of the constant and then factors of the leading term coefficient to start off with. So the constant is 2. So the factors of 2 could be plus or minus 1 and plus or minus 2. So not many factors there. The leading term coefficient it is 6, so it could be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So those are all the possibilities there. Now, according to the rational zeros theorem, all the rational zeros would look like a fraction of those numbers, so p divided by q. So if I just take all the numbers in my factors of the constant divided by all the numbers in the list for the leading term coefficient, that gives me all of my possible rational zeros. So, for instance, 1 over 1 gives me just 1, so plus or minus 1. 1 over 2, that could be plus or minus 1/2. 1 over 3, then plus or minus 1/3. And 1 over 6, so plus or minus 1/6. All right, if I go on to 2, 2 over 1 could be plus or minus 2. 2 over 2 is just 1, so that's already listed. 2 over 3, that's another possibility, so plus or minus 2/3. And then 2 over 6 reduces to 1/3, so I don't need to list that again. So these are all the possible rational zeros of my polynomial. It doesn't mean that any of them actually are zeros. It just means that if there are any rational zeros, it will be contained in this list. Let's look at an example finding all the zeros of a polynomial function p of x equals 6x to the 4th minus x cubed minus 24x squared plus 9x plus 10. Okay, so we need to start finding initial zeros. So that's what the rational zeros theorem is going to do for us. So I start by listing factors of the constant. The constant's 10, so it could be 1, 2, 5, or 10 itself. Factors of the leading term coefficient, which could be, since it's 6, it could be 1, 2, 3, and 6. And if I take all the factors of the constant divided by all the factors of the leading term coefficient, I'm going to get my list of possible rational zeros. So 1 over 1 could be 1. 1 over 2 could be 1/2. 1 over 3 could be 1/3. 1 over 6, so 1/6. All right, 2 over 1 could be 2. 2 over 2 is 1, so that's already in there. 2 over 3 is 2/3. And 2 over 6 could be, well, that would be 1/3, and that's already contained, so I don't need to list that again. All right, with 5, 5 over 1 is 5. It's possible. 5 over 2 is 5/2. 5 over 3, so 5/3. 5 over 6, so 5/6. And then with the 10, 10 over 1 is 10. 10 over 2 is 5, that's already there. 10 over 3 is 10/3. And 10 over 6, that would reduce to 5/3, and that's already in my list. So this is all my possible rational zeros. And this is a pretty lengthy list of possible rational zeros, and it can be kind of intimidating, the number of potential zeros that exist. And if you'll notice as well, a lot of these are fractions, and fractions tend to intimidate people. So what I'm going to do is I'm going to start testing integers and just see what integer zeros I can get first. And if I can get at least 2 integer zeros, then I don't have to test any of the fractions. I can get the fractions through factoring. So let's just see what happens. Let's start with positive 1. In order to find out if it is a 0 or not, I'm just going to use synthetic division, see if the remainder is 0. So the skill that we learned in the last section. All right, so here's my coefficients. I bring the 6 down. 6 times 1 is 6. This becomes 5. 5 times 1 is 5. Negative 19. That's negative 19. 9 and negative 19 give me negative 10. 1 times negative 10 is negative 10, and these add up to 0. So positive 1 is a rational 0. So that's great. That's 1 down. I only need a total of 4. So out of this entire list of possible rational zeros, only 4 could possibly be. Now, one thing that I want you to notice here is this right here represents a polynomial of 6x cubed plus 5x squared minus 19x minus 10. And at this point, if you'll notice, the leading term coefficient is 6, the end constant term is 10, is still the same list of possible rational zeros. So I can just continue on with the same list, but with my new polynomial, which is going to be slightly less work, maybe not a lot less work. So the next possible rational zero that I'm going to do is negative 1. So just try it. But I'm going to try it into the new coefficients, not in the original coefficients, because each time I find one, my work's getting a little bit easier. So bring the 6 down. 6 times negative 1 is negative 6. This becomes negative 1, positive 1, 18, negative 18, and oh, sorry, I just noticed this is a negative 18, which makes that a positive 18. Regardless, it's an 8 or a 28. Either way, it's not 0. So negative 1 is not a 0. And I tell you what, let me write in the zeros I have so far. Positive 1 is a 0. All right, so in my list, the next one to try is a half. But like I said, I'm just going to try all the integers first, and then I'll deal with the fractions later on. So I'm just going to try positive 2 into these coefficients. So if I bring the 6 down, 2 times 6 is 12. 5 and 12 is 17. 2 and 17 is 34. Negative 19 and 34 is 15. This would be 30 and 20. That's not a 0. All right, so I can also try negative 2. Let's see what happens. So 6, 5, negative 19, negative 10. Let's bring the 6 down. This would be negative 12 or negative 7. Negative 2 times negative 7 is 14. 19, negative 19 and 14 give me negative 5, which multiply to 10. Oh, and there's another 0. Okay, so I'm going to go up here and list negative 2 as a 0. And here's the thing about this, is this is now a polynomial 6x squared minus 7x minus 5. And its zeros are going to be contained in, if it has rational zeros, it's going to be contained in this list. I really don't want to go through and continue this list, and I don't have to because this is a quadratic, and I know how to factor quadratics. So I'm just going to try and factor this thing. So let's see what happens. So 5 is a prime number, so these two values here need to be 5 and 1. 6, there's a few different possibilities, but I've got to get this thing to add to 7. So let's just try different ones. So it could be x and 6x. That would give me 5 times 6 is 30, x times 1. That's not going to be any good. All right, let's try another possibility. Let's try 6x and x. So this would be 5x and 6x. So that would be 11. That's closer, but still not quite what I need. All right, but I could try, say, like 2x and 3x. So that's 15 and 2. Not going to work either. And I have one last possibility, 3x and 2x. That would be 10x and 3x. And that would be good, because if it is negative 10x and positive 3x, that's going to add to the negative 7x. So through factoring, I discover what these remaining zeros are. Well, I've got the factors, but I haven't turned them into zeros yet. But I don't have to go through any more synthetic division. To get the zeros, I just need to set this thing equal to 0 and solve. Well, to solve this, I split it up. 3x minus 5 equals 0. 2x plus 1 equals 0. And just solve for x. So x equals 5/3. 2x equals negative 1, or x equals negative 1/2. So there are my remaining zeros. So back up here to my list, 5/3 and negative 1/2. And I don't have to go through any more testing, because it was a degree 4 polynomial, and that guarantees that there's at most 4 zeros. So I have found them all. So this is basically the process. Check your degree, see how many zeros you need. Try and find enough initial zeros to where you can at least get down to a quadratic after factoring out those initial zeros. Factor the quadratic. This process is a little bit difficult, but if you notice, I didn't need the calculator at all. But let's see what the calculator can do for us to kind of help us out in getting those initial zeros. All right, so finding initial zeros on the calculator, we're going to first graph the polynomial, then use the zero function to calculate the location of zeros. That's the most accurate way. So again, you press second, calc, and option 2 is your zeros. So let's work with this polynomial right here, the one we just did, and see how the calculator can come up with those initial zeros for us. All right, so I'm going to graph my polynomial. So it's 6x raised to the 4th power minus x raised to the 3rd power minus 24x squared, or you could do caret with a 2, either way, plus 9x plus 10. Now, the window, let me make sure the window is set. It's changed. Here's what I'm going to do. I'm going to hit zoom, and then option 6 is zoom standard. So that just changes it to negative 10 to positive 10 on both the x and the y axes. All right, so here's a graph of my polynomial. Now, if we have a rational zero, this is what we learned in an earlier lesson. If we have a rational zero, it's the location of an x-intercept. So basically, I'm looking for x-intercepts. So let me zoom in on where my x-intercepts are. And the zoom box is what I'm going to use here, because that's the nicest feature in order to get, if you can see the things you're trying to calculate. So I'm just going to drag this rectangle, and it's going to reset my window so that I'm looking at these particular points. Now, if I have any integer zeros, so for instance, if you'll notice, like right here and right here, those are pretty easy to identify right off the bat, and I try and get those integer zeros first, and if I can get integer zeros, then I can, not have to worry about fractional zeros and just kind of get them, the fractional zeros, through through factoring. let's start off by calculating these zeros. All right, so second calc, oops. And option 2, which is a 0. Now, the left bound, even though I'm pretty certain, say like this one right here exists at -2, I'm going to go ahead and calculate just to make sure. So the left bound I'm going to give as, say, like -3. The right bound I'll give as -1. So negative, oops, I'll turn my coloring off here. So -3 for the left bound, -1 for the right bound, and the initial guess I'm just going to give as -2. And then let it calculate it, and turns out that is exactly my 0. So for my zeros here, let me label. So for my zeros, I have x equals -2, and then I see another one right here. Let's see what that is. All right, so second and calc, and oh, that's funny, I'll just leave it, the 0. The left bound, I'm going to put the left bound in as, say, -1, and the right bound in as 0. And the initial guess I'm going to give is -0.5. And that is what it found. So -0.5. The nice thing about that is we know that it's -1/2. Okay, so that's fine. And let's move on and see what else we can discover. So here's another 0 right here. That's probably +1, but always check because you never know if it's just off a little bit. And it's not difficult to calculate them. So I'm going to give a left and right bound of, say, 0 and, well, here's kind of an issue. If I put 2 in, I've got 2 potential zeros there. So I need to give something closer than that. So if I'm thinking it's 1, I think what I'll do is I'll give, say, like 1.5. So 1.5 should be like right there. So I'll give left bound of 0, right bound of 1.5. And the initial guess, I will give it +1. And the nice thing is, if there are 2 zeros on your interval, like for instance, if I gave it +2, there's a 0 here and a 0 there. The reason it's showing you that cursor is because it's showing you which one it's located for you. So it found +1 as a 0. All right, let's do this last one. So now the last one, if I do second and 0, or second calc and 0, here's what I'm going to do. I'm going to give the left bound as 0 and the right bound as 3, just so you can kind of see what happens when there's 2 zeros on your range. So left bound is 0, right bound of 3. And my initial guess, I'm going to give it an initial guess that's close to that value. So I'm going to give it, say, 1.5. I feel like that's close to that number. So it calculates, and it does find the one closest to 1.5. Now, if you'll notice, it's 1.6666667, and if you know what that rounds to, if you know how to change that into a fraction, you can just list it. Or we have enough initial zeros to where you can start factoring out using synthetic division on the -2, and then do it on the 1, and then if you factor out the -1/2, then you're going to get that remaining 0, which it actually is 5/3. And your instructors most likely going to want you to give that as a fraction. I don't think I know many instructors that will allow decimal answers unless your answers are irrational and the only thing you could give is a decimal. So if it is rational, you need to provide it as in fractional form. So that's how we use the calculator to get initial rational zeros. Just graph the function, look for the ones you can. I recommend just, get the ones that are integers and then factor those out. If you have just 2 remaining, just get it down to a quadratic and then factor. Now, sometimes you're going to be asked to express your answer as factored polynomial, and sometimes you'll be asked to give the zeros. So, same example, we already know what the zeros are. So, if you're asked to give the zeros, then you just list out what the zeros are. If you're asked to provide your answer as a factored polynomial, well, you just need to change those zeros into factors. And the way you do it, so if x equals 1 is a 0, well, if I bring the 1 over, I get x minus 1 equals 0. X minus 1 is my factor. Okay, so this is my factor. So you have basically the form of the 0, which is the x equals 1, form of the factor, which is x minus 1 equals 0. So it's pretty straightforward to turn any 0 into a factor, and vice versa. So like here, if I add 2 to both sides, x plus 2 equals 0 is what I get, and x plus 2 is my factor. It gets a little bit trickier when fractions are involved, but it still isn't too bad. So if x equals 5/3, start off multiplying both sides by 3. So 3x equals 5, and then bring the 5 over. So 3x minus 5 equals 0. So here's my factor there. So this was my factor, x plus 2, another factor, 3x minus 5. Likewise, if x is negative 1/2, multiply both sides by 2. So 2x equals negative 1. Bring the 1 over. So 2x plus 1 equals 0. So there's my factor. So the factored form of this polynomial is x minus 1 times x plus 2 times 3x minus 5 times 2x plus 1. So either way, you're generally finding the zeros first. So if you're asked to provide zeros as answer, you just list your zeros and that's fine. If you're asked to provide your final answer in factored form, then you just convert your zeros into factors and you're done. Now, there's a few different cases of how zeros can occur. So you could end up with all factors of your polynomial being rational. And so, therefore, they're all x-intercepts. You can find them using the calculator. But sometimes you have all but 2 factors are rational, which could mean that you have the last 2 being irrational, which means the square root's involved, or complex, or imaginary, meaning that you have I involved. But at least it's all but 2, so you get as many rational zeros as you can. If what's left over is a quadratic, you can use completing the square or the quadratic formula. You could have repeated zeros, which again, we'll discuss through an example. It's easier to show through an example. After all that, we're going to talk about how to simplify the process, because it does seem like this is a very time-consuming process. So we'll look at how we could possibly utilize factor by grouping to simplify the process, and identifying whether 0 or plus or minus 1 is a 0 of your polynomial function. Because if those are zeros, you can pull them out pretty quickly and move forward. Okay, let's start with some example problems. So beginning with p of x equals 6x to the 4th plus 17x cubed minus 35x squared minus 22x plus 24. First thing I want to do is find initial zeros I can factor out. I'm going to go to the calculator to do that. Okay, so we're going to graph the function that we have here. So I'll just type it in, 6x to the 4th plus 17x cubed minus 35x squared minus 22x plus 24. All right, double check it here. It looks good. And I'm going to graph it, but just in case my zoom is changed, I'm going to hit zoom 6 just to bring me into the standard viewing window. And what I'm looking for here are initial zeros that are integer based. The fractional ones I'll try and come up with later. So what I see here is right there, that looks like an integer based one, and right there as well. So I'm pretty sure I've got some initial zeros of -4 and -1. So let's just see what happens if I factor those out. Now the thing is, one of these might not be right at -4 or -1. It could be like -4.0001, whatever. It probably isn't, but it is a possibility. But if that happens to be the case, when I do my synthetic division, I won't get a remainder of 0 in the end. So I'm kind of proving that it's a 0 here as well. So I'm going to factor these out. I think I'll start with the -1, just because it's a smaller number. All right, synthetic division here. Bring the 6 down. 6 times -1 is -6. Add that to the 17, you get 11. Times -1 is -11. Add that to -35, that's -46. So positive 46 here. 24, -24, and 0. Since that remainder is 0, I'm certain that this thing is definitely a a 0. I don't have to worry that it was -1.001 or anything like that. Okay, now let's factor out the -4. And remember, I only have to factor it out of the remaining polynomial, which is a little bit easier because it's one less number to work with. So bring the 6 down. 6 times -4 is -24. Add that to 11. I've got -13. Times -4 is 52. Add these together to get 6. Then -24 and 0. So this remaining polynomial here is 6x squared minus 13x plus 6. And that's what I want to figure out the zeros of at this point. If I can find the zeros of it, then I'm done. Because it's a quadratic, I can try and factor. And I think I will try and factor this. So let's do it like this. So 6x squared could be 2x and 3x, or 3x and 2x, or 1x, 6x, so forth. A bunch of different options. I'm going to try 2x and 3x. And then for the others, I think I'll just try 3 and 2, see what happens. Hopefully I will get lucky. So 3 times 3 would be 9, 2 times 2 would be 4. Actually, that works out perfect. I did get lucky here. So we've got to make sure they multiply to positive 6 and add to -13. So there's the remaining zeros. So if I set each of these equal to 0, so 2x minus 3 equals 0, 3x minus 2 equals 0, so 2x equals 3, or x equals 3 halves, 3x equals 2, or x equals 2/3. So there are my remaining zeros. So -4, -1, 3/2, and 2/3. So in that situation, all of my zeros were rational values. And so if you'll notice, I did have 4 places where I crossed the x-axis. The 2 that I just found, right here and right here, that's the only reason I didn't pull those initially off the calculator screen is because I knew they were non-integer. And so I feel like it's easier to find the fractional ones through factoring, but you know, you're certainly fine to use the zero function to come up with what those are as well. Just make sure to write your final answer as a fraction. Okay, another example here. Let's find the zeros of the polynomial function x cubed plus x squared minus 7x minus 3. All right, so again, we start off by finding initial zeros. So let's see what we can do with the calculator. X cubed plus x squared minus 7x minus 3. If I graph that, okay, I definitely get one value that's integer based. Looks like right there. So that's going to be at -3, it looks like. So let me factor that out and then just see what happens at that point. So pretty sure I have a zero of -3. Let's go through the synthetic division, see what happens. So 1, 1, -7, -3. If I bring the 1 down, -3 times 1 is -3. Add that to 1, this is 6. Or -1, +3, and 0. Okay, and it is. Now, the others are non-integer based. So what I'm going to do, instead of solving for them using the calculator, I'm simply going to solve for them using factoring or whatever process I need in order to come up with the answers, because my remaining polynomial is now quadratic, and I have a lot of ways of solving quadratics. This will not factor. You can try different possibilities, but it turns out it will not. So instead, what I'm going to do is go the route of completing the square. So I'm just going to move the constant to that side. If I take -2 divided by 2, that's -1. Square it, I get +1. So this factors into x minus 1 quantity squared, and that's equal to 2. So x minus 1 equals the plus or minus square root of 2, or x equals 1 plus or minus the square root of 2. So those are my remaining zeros. So -3, and 1 plus or minus the square root of 2. So I did come up with 3 zeros. There's just one zero is 1 plus the square root of 2, and the other 0 is 1 minus the square root of 2. So that gives me the 3 that I needed, because this was a cubic polynomial. All right, another example here. And again, I'm going to bring up the calculator and try to get initial zeros to start off with. So clear out what I was just doing. So this is going to be 4x cubed minus 3x squared plus 16x minus 12. And graph that. Okay, looks like I'm only going to get 1 0 here. I think it's at +1. I think I can see that at +1. I'm not totally certain, but again, if it's not actually at +1, then I'll find that out through the synthetic division. So let's just see what happens. So plug in 1, so 4, -3, 16, -12. All right, so bring the 4 down. This would be 4, 1, 1, 17. Ooh, it's definitely not a 0. Okay, so let's look a little bit closer here. Let's go back over to the calculator screen. All right, So I can see that 0, but let me solve for it. So if I do second calc and 0, left bound I'm going to say 0, right bound I'm going to say 2, and then I'm just going to make my initial guess as 1. Ah, there it is. Okay, there's the issue. So the 0 it found is at 0.75, which is 3/4. All right, so that means my initial 0 is 3/4, which is close to 1, but not exactly 1. All right, but I can do synthetic division on the 3/4 just fine. So 4, -3, 16, -12. So bring the 4 down. 4 times 3/4 is 3. That adds up to 0. 16, 3/4 times 16. 16 over 4 is 4. 3 times 4 is 12. Add those together. And this is now a quadratic, which looks like 4x squared plus 16 equals 0. Or 4x squared equals -16. Or x squared equals -4. Or x equals plus or minus 2 times I. So what's happened here, my remaining zeros were actually complex values because on the calculator, if you'll notice, they never came back and crossed the x-axis. So if you don't cross or touch the x-axis, you don't have a real 0. You have a complex 0, and that's exactly what's happened here. Okay, I think it's time now to mention what's called the conjugate zeros theorem, which states that if p of x is a polynomial function with real coefficients, and z equals a plus bi is a 0 of p of x, then z equals a minus bi is also a 0. So when we solve for zeros that are complex or even irrational, we always end up with that, plus or minus bit. Like in the last example, we had plus or minus 2i. So this just kind of confirms for us that these are always going to occur in conjugate pairs. So if you get one complex 0, you also have the conjugate of that 0 as well. So some ways this is used, like for instance, factor p of x equals x to the 4th plus 10x squared plus 9, given that x equals I is a 0. Well, if I know x equals I is a 0, I can factor it out. And you might be thinking that this is going to be more difficult because I'm using a complex value. It doesn't have to be, and you can always use the complex features of your calculator to help you out if you need. Well, let's try it without. Let's bring the 1 down. 1 times I is I. 0 plus I is I. Now I times I is -1. 10 minus 1 is 9. 9 times I is 9i. If I add that to 0, it's 9i. 9i times I is going to be -9. All right, now, the thing about this is I'm also guaranteed that -I is a 0 as well. So I can take this remaining polynomial and factor that out here. So let's try it. So bring the 1 down. 1 times -I is -I. This adds up to 0. That's 0. That's 9. -9i. These add up to 0 as well. So this right here becomes x squared plus 9 equals 0, or x squared equals -9, or x equals plus or minus 3i. So I've come up with my zeros here. Plus or minus I and plus or minus 3i. So this was kind of an interesting problem in that all the zeros were complex, but we were still able to solve for it. Now, that actually wasn't the only way that we would have been able to solve for it. Another way that we could have done is through a process of U substitution. So if we have x to the fourth plus 10x squared plus 9, we're trying to find the zeros of this. If you let u equal x squared, just like we saw in an earlier chapter, we could write this as u squared plus 10u plus 9 equals 0. So factoring this, I get u and u, 9 and 1 would multiply to 9 and add to 10. So u plus 9 equals 0, and u plus 1 equals 0, which would mean u equals negative 9, u equals negative 1, or x squared equals negative 9, and x squared equals negative 1 when I substitute back. So x is plus or minus 3i, and x is plus or minus I. So don't forget about processes from earlier also being able to apply as well. All right, another example here. Find the zeros of x cubed minus x squared minus 8x plus 12. So I'm going to graph it first. So x cubed minus x squared minus 8x plus 12. So, graphing it. It looks like I've got some initial zeros here. One there and one there at negative 3 and positive 2. All right, so let's see what happens here. So I'll start with the negative 3. Okay, so 1, negative 1, negative 8, and 12 are my coefficients. Let's bring 1 down. That's negative 3. So this adds up to negative 4, 12, 4, negative 12, and 0. So that definitely is a 0. All right, now let's try 2 into the remaining. So 1, negative 4, and 4. Let's bring the 1 down. This is 2, negative 2. That's going to be negative 4, and that's 0. This remaining polynomial, if you'll notice, is actually x minus 2 equals 0, or x equals 2. So here's the interesting thing about this problem. So we knew that there was supposed to be 3 zeros because the degree was 3. And we only found 2 initially on the calculator screen. But one of those is a 0 2 different times. So we actually say this is a 0 of multiplicity 2. So it occurs twice. And that gives us the third 0. So it's basically negative 3, 2, and also 2 again are the 3 zeros. So they were all real numbers, and that can happen. You just have to watch out and know that if you don't get enough initial zeros to get your polynomial fully factored, or at least down to a quadratic, try plugging in your zeros again to see if any of them were zeros of multiplicity. Okay, so certainly this is a fairly difficult process. It's time consuming. So let's look at ways of making the process easier. Factor by grouping. This is a method that we learned factoring early on, where if you have 4 terms, you can factor it if it will factor, you can factor it by grouping. So here's a polynomial with 4 terms, and we saw it earlier as an example. And let's just see what factor by grouping can do for us. So factor by grouping says to take the first 2 terms, group them together, and the second 2 terms, and group those together, and pull out a common factor between each group. So I can pull out an x squared, whoops, this was an x cubed. Let me just do that right there. So that leaves me 4x minus 3. And in the second group, I can pull out a 4, which would also leave me 4x minus 3. Now here's the important thing, that this piece and this piece match, because that now factors out as its own part. And it's going to leave me with x squared plus 4. So without any work plugging into the calculator or anything, we've already found one of our zeros here as 3/4. From this polynomial, I can set that equal to 0 and come up with x equals plus or minus 2i as the remaining zeros. So the zeros of this polynomial are 3/4 plus or minus 2i. So with that factor by grouping working for me, I didn't actually have to go through any much effort at all. Definitely a lot faster process. All right, one thing that can help you out is if 0 is a factor. Now, if 0 is a factor, it's pretty evident because x has to be a common factor among all your terms. So you can't have a constant term in your polynomial and have 0 being a factor. So in this case, x squared is common to all of these terms. Okay, which leaves me with a quadratic and probably one I can factor. Let's see, 3x and x, that definitely has to be the first 2 terms. And then 20 could be 4 and 5. Then I think I could make that work because this would be 15 and 4 if the 15 is negative and the 4 is positive. So then my zeros here. 0 is multiplicity 2. That's important because we're supposed to find 4 zeros. So that's 2 of them. Negative 4/3 is another one, and positive 5 is the last one. So there's all 4 zeros. Another way to make it easier is identifying if plus or minus 1 is a factor. And so the way you can think of this is, like, if you plug in x equals 1, well, no matter what you do, if you square 1, cube 1, raise 1 to the 4th power, you're always going to get 1 back out. So evaluating a polynomial function at 1 is actually pretty straightforward. You're basically just adding the coefficients. So if you just add up the coefficients, 1 minus 1 is 0, plus 2 results in 2. Well, it's supposed to result in 0, so that's not a 0. Let's try negative 1. Negative 1 also isn't all that difficult, because if you put it in to an even powered, it results in positive 1, and odd power just results in negative 1. So you're basically just going to either do the opposite of your value of your coefficient if it's connected to an odd power term, or the same if it's even. So like negative 1 to the 3rd would be negative 1, minus negative 1 squared, so it's just going to be minus 1, it'll be the same, and then plus 2. Well, negative 1 minus 1 is negative 2, plus 2 is 0. So it turns out we've already got a 0. We didn't have to get the calculator out or do much work. We do have to factor it out to figure out what the new polynomial would look like. But once you get used to this, it does save you some time. Or it can save you some time. All right, so this is the remaining quadratic, x squared minus 2x plus 2 equals 0, which is one that we won't factor, but I'll just use completing the square here. So if I take negative 2 divided by 2, that's negative 1. Squaring it, I get positive 1. So this factors into x minus 1 quantity squared equals negative 1. X minus 1 equals plus or minus I, or x equals 1 plus or minus I. So the zeros of this polynomial are negative 1 and 1 plus or minus I. And there's all three of them.